Hi people, I'm going to present you a case that I'm working on. First, just giving the context before I get into the presentation. This is a fraud detection problem. It's a data set from Kaggle, and the issue here is we have a lot of data, a lot of features, and then we have to predict the probability of a transaction being fraudulent. Uh, First, we don't know the reasons for the fraud because this is a Kaggle dataset. It's less toy data than some other datasets, but still it's not exactly a real-world problem, so that we would have to define the target variable and other stuff. So we don't have this business understanding so much, but still we can solve this problem, and this is I believe that this might work as a template for solving cases, maybe. And so let's start. Here we have this data set. It is really large. It has more than 1 GB. And we have a lot of features. They don't have too much definition, so I won't do so much exploration about them. But anyway, let's start the presentation. Oh, and other thing, I'm not going into the notebooks, but they are saved on GitHub. I can give the link further. And on those notebooks you can see more details, more visualizations about some exploratory data analysis of all features, and but I didn't put all that on the visualization. My idea was to, okay, what am I trying to solve, and what solution can I give to stakeholders? So let's start the presentation. So to summarize my presentation, I'm going to start with an introduction about the problem, some EDA, then feature engineering, modeling, and strategies. And well, about good practices, it's always good to start with an MVP. We don't want to take too much time building a complex model. So what is the minimum viable product that we can start with? And the idea of Six Sigma, we should focus on delivering as much value as possible, but not going too deep on that because there might be other priorities for projects. And the idea of separation of concerns is related to my notebooks, the way that I try to separate them in different modules so that it gets easier to for collaborative work and to debugging. And about the data cleansing part, there was a lot of missing values, and I used some threshold for removal. For column removal, I consider a 30% threshold, and for the rows, I consider a 50% threshold to remove them. And it will be hard to assume beforehand if we have missing at random data or missing not at random. I cannot make any assumption for now because I didn't have time to explore that. But for now, I'm considering that it's at random. So that makes it easier to take some decisions such as, okay, how are we going to impute the missing data? And so I used median for that, for the continuous data, and the mode for categorical data. And I wanted to use KNN, K nearest neighbor, but I didn't have enough time because of there are so many features that it required a lot of, I didn't have so much speed to solve that. And we had a lot of features. I should place the number of features here, but there were hundreds of features. but most of them had too many missing values, and they were not interpretable. About outliers, I used that for annotating data. I used isolation forest algorithm, and I took more than 1,000 outliers to annotate, but I didn't have a rationale to remove them. You really need to justify, because some outliers might be just some errors, and you can try to get in touch with data engineers and other data curators to deal with that. Or you can, well, you need to justify the removal. Well, those are some box plots. Here we can see that there are some huge outliers, so the box plots get really narrowed, for instance, for those variables. Some distributions, I didn't find yet a good definition of the categories in the categorical data. But we can see here that depending on the category that you have, it can have some result on your target variable. And so what I mean here is 0 is when you don't have fraud, it's normal cases, and 1 is when you have fraud. And about the cards, you have some different data about the cards that are being used. And for the discover flag, you have more cases of fraud than in some other flags. And for credit, you also have more fraud. Here are some distributions. They don't seem very clear about differences for fraudulent behavior. In some cases, when we have a clear visualization, some of those distributions, for instance, the blue one about the fraudulent cases, it will get more skewed in one direction. And here, it's the same thing. It doesn't seem too clear for me. About imbalance, well, we have a hugely imbalanced data set. We have 96 cases of normal transactions, 96% compared to 4% for fraudulent transactions. So we must tackle this later. About feature engineering, I did some encoding, ordinal encoding, when I wanted to use 3 models, and 1 hot encoding for linear regression. There are some assumptions for the reason of using different types of encoding. For feature selection, for checking for multicollinearity that is important for linear regression, I used VIF. But we need to be attentive to nonlinear relationships, also for visualization purposes. Feature importances, we can have that on 3 models. And here are some correlations. It's not clear for now any clear correlation here. Remember that here it's a linear relationship, except for card 3. And well, here are just some multicollinearity issues. About feature selection, I tested 2 different combinations. And for feature importances, I compared 2 models with the XGBoost. On the right, we have all features, and we get this F1 score, that is the score of interest that we are using. And on the left side, we reduce the number of features, and we sacrifice just a little bit of the F1 score. So I would prefer this model because he is a little more explainable. We have fewer features to use. And I know that maybe we should have, for a template we should have a more explainable model. It will be better. Maybe I'll try another data set for working. About modeling, well, first thing first, we need to consider the Occam razor. The simplest solution is usually the best one. And the algorithm of choice will depend on prediction score, explainability, time of development, how long it takes to develop this, computational cost and reproducibility. For instance, if we're using state-of-the-art models, they might take longer and they might be less harder to reproduce and to deploy also. And we need to consider the learning curve of using some complex algorithm too. So the choice depends on the business problem and stakeholders' knowledge. And about the score metric, I used F1. It is the harmonic mean between precision and recall, and we can calibrate the weight between precision and recall later. And for validation, I used well, the rule of thumb: prime validation test split, k-fold cross validation, hyperparameter tuning. For models, I used baseline with logistic regression without tuning the hyperparameters. Well, logistic regression, random forest, and XGBoost. So for model selection, and here I don't have necessarily the different machine learning models, but different machine learning models with different combinations of features or some preprocessings. For instance, I have 3 XGBoost models, one with a selection of features, one with a selection of features and weighting of the imbalance. So you can choose to use SMALT or other type of algorithm, but I'm using some built-in structure inside the XGBoost to correct imbalance. And this is the XGBoost with all features. And this is the train time comparison. And oh, sorry, I need to correct this. And this is the prediction time comparison that it should be important for example, if you are going to use your model for a mobile app or for in the browser for users, and it must be fast. And my choice, I chose this model, the selection one without weighting, because I didn't want to weight too much over the false negative issue. I know that recall is important, but I don't want to sacrifice so much precision, and I want to calibrate that manually after choosing the final model and final hyperparameters. So this is the result, the XGBoost with the selection of features, the features related to card and the C features that I can try to explain later. And here we have a validation with an F1 score of 466. And on the test set, the F1, it's a bit lower than the validation. So this might raise a red flag about why is it happening? Why is it not so closer to the validation train set? Maybe I got some overfitting. I will need to check later. And accuracy, well, we are not interested in accuracy. It's misleading on that case because of imbalance. But these are the metrics, the other metrics that we got: the recall, the precision, the logarithm loss. Well, this is just a sample comparison of estimation of true value and the predicted value. So it seems good for that sample. Histogram of probabilities, this is imbalanced, so I will predict on most cases that the probability of a fraudulent transaction is extremely low, but we have some other cases here of high probability. And about strategy, this is, I think, the hardest part on data science. In a real business problem, we have to consider some key metrics, some business metrics that we're going to use. Instead, in Kaggle, we just use machine learning metrics. So I wanted to get some, instead of focusing on the score, I want to focus on how do I deliver this as a recommendation. So we don't have business metrics here, so I'm using some assumptions that we can change after we get the precise metrics for that. So I'm going to consider that as the median cost of fraud, it is 5,000. So how much the company loses from a fraudulent transaction, and that the median remaining lifetime of users after we detect fraud and we bother that user on refusing the transaction, so we might get some churn over him. So his median value is 1,000. And here I get the precision recall curve, and I see that the precision falls really fast when we try to get high recall. So this is a hard data set. This data set is really hard to tune, and we must make hard choices. We don't have good score metrics. So I will choose not so high recall because I don't want to sacrifice precision so much. And so on the left side we have the precision recall curve, and on the right side we have the score number of covered cases. And we separate precision and recall. And we see that, okay, precision falls really fast and recall doesn't grow so much. So we must be careful on considering the trade-off. And so about the strategy, the theoretical baseline, considering that, okay, let's consider that we have 80% true negatives and 40% true positives, and considering that value that I explained before, those values. So we would have here the number of true negatives, true positives, we would have this number, this total value. And by calibrating the threshold for 50%, 30%, or 15%, we can, by doing that, we can calibrate recall. We can get high recall but lower in precision, and so we get more true, a few less true negatives, but we also can lower the number of false negatives that are extremely costly for the company. And so here I'm just comparing how much improvement do I get about that value from 1,000 observations. I have those numbers of true negatives, normal transactions correctly classified, normal transactions misclassified, and so on. And so here for the comparing the baseline of the machine learning model that I chose with a threshold of 50%, I get 18% improvement over the theoretical baseline. This is just the confusion matrix. For the other thresholds, and here I'm just going to show the final threshold, that is 15%. So I get a bit better improvement, 19% improvement over the theoretical baseline, and a really small improvement over the first threshold, just 1.5%. So maybe we can use the first one, but I'm going to consider this one as the final threshold with the XGBoost model. And just doing a stress test, what if we set an aggressive threshold of 0.01%? So if there is a really low probability of the transaction of being fraudulent, we will just flag it, okay, this is fraud. And what will happen? Well, we might reduce a lot the number of false negatives, so we are going to catch all fraudulent transactions. But we are going to have a lot of false positives. we're going to flag everything as fraudulent. So this will be really costly. We're going to lose a lot of normal transactions. So is this a good strategy? No, it doesn't seem so. And why so? Because we are sacrificing too much normal transactions to get, if we want to get zero fraud. So it's not worth doing that. So we need to choose something in between the number of false negatives and false positives. And that's it. This is just my first presentation that I'm recording. I hope you enjoy it. And well, I want to keep improving, and I'll stay building other use cases. See you later.